All right, folks. So today we're going to be looking at finding the volume of a solid, one function still. We'll spend a couple days on this, and then we'll eventually go to two functions. But today we're still working on one function. But what makes today different from the previous 2 days is that we are no longer going to be revolving these regions of area, these areas of regions around or about the x-axis. Okay, it's not going to be that simple. It's going to be revolving around a certain line, y equals, we call it k, right, for a constant. Okay, so let's do it like a very basic one first, right? So let's look at number one. Okay, so this is the function. This is the function y equals x plus 3 halves. Okay, and we have also x equals 2 and the x-axis. So basically when we graph it, you can use a graphing calculator if you like. If you want to do that, that's fine. Um, you can go, let's see, y equals x plus 3 halves if you like. See, now you can't graph x equals 2 and the x-axis. So I mean you can do certain things, but let's just say you do that, right? I'm going to zoom and do a 6 on that, and that's basically just that line right there. So let's just do a quick reconstruction of this. So this is a y equals mx plus b equation. You're going to go ahead and graph this. The starting location or the y-intercept is going to be at 1.5, right? So 1.5 is right here. That's 3 halves. And the slope is up 1 over 1. So it's going to go like this, right? So this is our equation. That's our y equation. Okay. X equals 2 is right here. So this line right here. That's x equals 2. And then the x-axis is, let's call this x equals 2. And the x-axis, this is down here. Okay, x-axis also known as y equals 0. Okay, so we want the region surrounded with those three pieces. So what we're talking about is we want this area right here. And that area, and we're going to do a couple things with it. Okay, first off, and I'm not giving you guys this assignment this year because I'm utilizing this to kind of help us with our notes. But first, we're going to revolve this around the line y equals 0. So basically, y equals 0 is this green line right here, the x-axis. So we're going to revolve around the line y equals 0. So this is actually what we've been doing for the last couple of days. Right? So this is what we've been doing for the last couple of days. So if we do that, okay, let me kind of just clean this up just a little bit. We have that region, that right there, and that right there. I'm going to revolve that around that line right there. Okay, so when we revolve it, we're going to end up with something that looks like this. My drawing might not be the best, so, but you get the idea. Okay, and so it's going to create that shape. Okay, what shape does it look like? Well, it's going to create that. Actually, I shouldn't do that. Okay, so it's going to create this shape. Okay, so what does it end up looking like? Well, it's basically going to be just like a cone, right? It's going to end up just looking just sort of like a cone. So it's going to look like that, and it's going to look a little deeper, right? So it's going to look kind of like this. Okay. So that three-dimensional shape. So if I was kind of drawing on the side, it would look kind of like this. So we end up kind of looking like that, right? If you need to pause it and take these notes or write them down, you go ahead and do that. Right? But it will look like that. It will look like just like a cone, except it's solid. So what we want to do is we want to cut a slice of it. We want to take a cross-sectional wedge of it. So we take a cross section, it would look like this. Okay? Which really going to end up looking like this. So your job is to figure out what is that cross-sectional area, or what shape is that. And if you look at it, it's just it's just a disc, it's just a circle, right? So that area for that circle is pi r squared. And remember, the r is the length from the center to the outside, and it's easy. We can go any way, right? We can go radius is this, right? That's not going to help us. Well, the radius is this. That's not going to help us. Okay? What's going to help us is if we consider the radius to be that right there, the vertical distance. Okay? Because we already know that that distance is from here to the outside of that function. Okay? So we know that, oh, that last one wasn't correct. We're actually talking about that distance here, okay, which is the same thing. So that's going to be pi r squared, and that r is going to be the length. That's r right there. That's the length of x plus 3/2, because that's the value of y. So that's what we're looking for in this case right here. All right, so I'm going to go ahead and erase all that. Hopefully, if you need all this, pause it. Oh, actually, I need all that. I'll write it on the side. I'll get rid of this. Okay, so we need to write down the integral. This is for part A. Integral is from, and in this case, we got to figure out what that point right here is. But integral is the, you know, or the, excuse me, the volume is going to be the integral from A to B of the area A of x dx, right? So the area happens to be a circle, which is going to be pi r squared. So we're going to use pi. The radius is just going to be x plus 3/2 dx. Okay. Pi r, oh, forgot the square, pi r squared. And then we need the upper and lower limits of integration. So let's go and look at where that's at. Okay, so we do know that our region, our original region, okay, our original region does go all the way up to 2. So we do know that our upper limit of integration is 2. But what's the lower, right? So you can utilize your calculator for that, or you can just, just use mathematics to solve it. You can say, well, at this point right here, I don't know what that point is, but at that point right there, the y will be 0. So this equation here, the y would actually be 0. So what would x have to equal? And the x would be, if we solve for that, right, 0 equals x plus 3/2. All we have to do is subtract 3/2, and x would equal negative 3/2. So our lower limit of integration is going to be negative 1.5 or negative 3/2. I'll put negative 1.5. Just keep it easy. Okay. So that is our integral. And in this one, we're supposed to just use the integral. We're not supposed to evaluate it. So if you want to use a calculator to evaluate it, but all good. Okay, so that's part A. Actually, I'm going to put all these in. I put all those in black just to make it look a little easier. Okay, so that was the last couple of days, right? And you guys have been doing stuff like that for the last couple of days. So nothing big, right? Nothing big. Mm, let's see. So what we're doing today, and that took us a little bit of time. What we're doing today is we're going to revolve these not along the x-axis or the line y equals 0. Okay, that's what we've been doing the last couple of days. Today we're going to start revolving these around the line, maybe above or maybe below. Okay, and I won't ever give you, and you may get that in college, but I won't ever give you a line that goes through that region itself. So this first one, so this next one, okay, B right here. Okay, we want to revolve this around the line y equals -1. So you got to figure out where's y equals -1. So here's your xy axis. Here's -1 down here. So the line y equals -1. If we're going to revolve around that line y equals -1, talking about this line right here. So we're going to spin this shape around the line y equals -1. Now slow this down and repeat it if you need it to. Okay, or if I go a little too fast. So remember, we're talking about this region here. Okay, this region right here. This area right here. Okay, if I spin this or revolve this around the line y equals -1, what would it end up looking like? Okay. Well, what it's gonna do, and I need to go down just a little bit more, is it's actually gonna reflect that down here a little bit more. So that shape, you see how there's a gap right here, right? There's a gap right here. Well, there's also gonna be the same gap right there, right there. So it's actually, put that aside for a bit. Okay. So it's actually gonna start not right with the green line because we're revolving it, but it's gonna have a 1 unit gap, and then it's gonna start there. So it's gonna do something like this, there, and basically all I'm doing is I'm just gonna copy that down. So try my best to do a decently good job of it, but it's gonna look like that. Because it's gonna revolve around that line. Oh, that line is gonna be y equals -1. Okay, so what it does is it actually creates this shape right here. So it's gonna swoop out. I'm just gonna get rid of this line right here. So what it does is gonna swoop out this shape right here. So that's gonna be the outer edge of it. And then in here, it's gonna create itself that, because that's all gonna be hollow. So this is all gonna be hollow. And behind there, it's gonna be invisible. You can't see that, but that's gonna be hollow right there. Okay, and obviously you can't see any of this right here. So this might be the end of it, right? But that's a shape it's gonna create. So it's gonna look something like, so I'm just gonna draw it three-dimensionally like this, like that. You can't see the inside of it, and like that. And it's gonna be like this, the outside, and then the inside you'll see like a little hollow. Okay, so it's gonna create that kind of three-dimensional shape, and that's all gonna be hollow right there. Okay, so this is gonna be your first instance of what we call a washer or a donut, right? So well, we have that three-dimensional shape, and we're going to take a cross section, right? We're going to cut a cross-sectional area. So anywhere you want, so let's just say somewhere kind of towards the end, because I don't want to draw that big of a circle. And take a cross section. It's going to look like this, a cross-sectional area. So that's going to be the outer edge of it, and this is going to be the inner edge of it. Okay? So that is a cross-sectional area, or at least my slice of this. Okay, but as we look on in three-dimension, or not in three-dimension, if we look at a flat, right, flat right on, what does it end up looking like? Well, it's just a donut, right? It's just a washer. Now the hard part, and I want you guys to pause it or rewind it or review it if you need to, is we need to figure out how to find the area, because remember, any kind of volume is basically just going to be the integral of the area of this cross-sectional area. This cross-section is going to be all of this right here. Okay, not counting the stuff on the inside. It's going to be all of this except the inside part. This is the hard part for a lot of people. So you got to take it slow and think about it, right? So if we look at that, how would we find that area of this donut or this washer, right? So the technical term that we use is washer. And if anybody works on machine parts or works on cars, you know that there are washers that um, that are part of a bolt or a screw set. So, but as far as washers are concerned, I mean, you think about it, okay? It has this outer circle, right? And and basically it's everything that's in there. So basically it's like this. And how do you find the area of this? Well, it's just a circle. It's just A equals pi r squared, right? Whatever the r is. So the radius, and again, we're going to use the one that goes up because it helps us the most. Okay, we can use that one right there, that radius. That's not going to help us. Okay, so we want to use the radius that goes up. So from the center out, okay, and since there's going to be another one, we'll call that capital R. So that right there, that's going to be your radius. So that right there is the area is equal to pi, and since we're using capital R, this will be pi capital R squared. Okay? Now, how do we find the area of this washer? Well, we got to find the area of the whole thing, or the big R, the big radius. But what we also got to do is we got to cut out the area of the little circle. And we need that right there. Okay, which makes a little area or a little radius right there. And that right there, okay, we got to cut out the small circle, and that right there is an area, which is pi, and that's a small radius, so we're going to use little r squared. So essentially, we end up with pi big R squared, and we're going to take out the small circle pi little r squared, and that's the area for that donut. So the area of the donut is pi big R squared minus pi little r squared. So the washer, any kind of area, is going to be pi big R squared minus pi little r squared. And to make it a little simpler, you can factor out the pi's, because if you think about it, you can have these together, but you're going to go ahead and factor out the pi's because that's what's the same. So you can take the pi's out. So what's going to happen is you're going to end up with something called pi parentheses big R squared minus little r squared. And that will be your area of that donut. Okay, review it again if you need to. Okay, rewind it or track back to an earlier time. So for that right there, once we figure out the lower limit, upper limit, all that good stuff, okay, hope you got this, or you can rewind it back. I'm going to erase it all. That was some good drawings right there, but yep, you don't take a picture of it or make a video of it, it's gone. Right. So for part B, we want to find the volume, and it's still going to be the same upper and lower limits of integration. So it's still going to be negative 1.5 to 2, but then the area of that cross section is going to be pi big R squared minus little r squared, right? And big R, so if we look here, right, what will be from the axis of rotation, what would it be to the top of the function? That would be big R. So big R is actually that top function, which is the x plus 3/2. So big R would be x plus 3/2. Here. Big R squared minus little r squared, right, dx. Right. What would little r be? Well, little r be from the axis of rotation to the inside, which is going to be right there. And that right there, if you look at what I'm doing right now, wherever I'm at, it's always going to stay the same because that's always a radius of 1. So little r equals 1. So in our case, we're going to have integral from negative 1.5 to 2 of pi, and big R is going to be x plus 3 halves squared minus little r is going to be 1 squared dx. Okay. As you work on it, you can move the pi through the integral like letter A. I could have done that, but I just didn't do it. So you will have the integral of, or pi to the integral of negative 1.5 to 2 of, now you have x plus 3 halves squared minus 1 squared is just 1, so I'm just going to write that down. So this will be your integral. And if you're going to do this in your calculator, you're going to go ahead and just type it in just like that. Okay, so that's from below. Okay, let's do another one from below. So let's do D. So D would be, you're going to revolve this around the line y equals negative 5. Okay, so I'm going to erase all this. If you need to, take a picture of it, or you know, pause it and put it into your notes. Okay, it's gone. It's going. It's going. It's gone. Just kidding. All right, so all of that is going to redo all of that. Give me a second. Okay, so all of that is gone. So our area to start out with, or our region, it's going to be this one right here. Okay, remember it's this region right here. It's all of that right there. Okay? And what we want to do is now, for part D, we don't only want to revolve it around the line y equals negative 1, but we want to revolve around the line y equals negative 5. So that's negative 1, negative 2, negative 3, negative 4, negative 5. Oh, you know what? I see the next problem. I'm going to go ahead and remove that just for our viewing pleasures. All right, so we're going to revolve it around the line y equals negative 5, which is down here. So we're going to spin this or revolve it around that. So what kind of shape is it going to make? Well, I'm glad you asked. Right, so it's going to make this big old gigantic shape. Right? So if this is 1, 2, 3, 4, 5 units, then it's going to actually reflect this down here. 1, 2, 3, 4, 5. And it's going to make this big old shape right here. So again, I'm just kind of eyeballing it, right? Because the exact shape or exact way that it's drawn is, it doesn't have to be perfect, but it's going to look kind of like something like this. Okay, because that's going to be revolved, it means it's going to reflect. So what you're going to have is, this is solid, right? Remember when I did earlier, all this was solid. So when I revolve it around, okay, it's going to create this. And this backside is, you know, right here, you're going to see that it comes out like this. Okay, and then this right here, we won't be able to see anymore. You can see that line right there, and that line, that's going to create the hollowness. And this backside is going to end up looking like this. And then this right here is going to create a little hollow to it. And this right here is going to be your hollowness. Okay? So ideally, you get some shape that looks like this. Like that, like that, like that. So it's just a little better drawing of it. So that's what it looks like. But then inside of it, it's going to have a hollowness like this. And it's all hollow throughout. Okay? So you won't see this, but this is all hollow through there. So if I was to cut a wedge from it, or slice of it, what would it look like, right? Well, obviously that's a slice of it. It would kind of look like this. It would look like this. And then it will also have this little hollowness to it. So not very good looking, but you get the idea, right? So you have, and I'm gonna draw a little better now. You have this. So that's the other side of it. So it's a round disc. Then it also has a little hollowness. So it's gonna look like this. That's the inside of it. If you can imagine that, right? So this actually looks, just like a big old washer. That's the best I can explain it. It's just a big old washer. So if you were to look at it head on, like from that direction, what would you see? So you would see something that looks like this. Of course, it should be nice and round, but it actually looks just like the last one, except it's just a bigger interior. And when we look at it, well, we will still from the center or where the axis of revolution, we still will have our big R, which is still going to be, oh, you know what? I think I messed up on the last one. Well, we'll go on from this one. So our big R is going to be from the radius on, okay? And then we still will have our small r, which is going to be from here on out. We'll call that our small r. Okay? Small r, if you look at it from our diagram, it's going to be from here to the center, and that right there, again, wherever I move it, that's going to always be 5, right? Because that's how hollow that is. So small r will just be 5, just like how our last problem, it was just 1. So this one is 5. Big R, you think about it, okay, we have all of this distance, which is already 5, and then you have this extra distance here. So it's not just 5, but it's not just what's the function? The function, it's not just x plus 3 halves, okay? Because x plus 3 halves is actually up here. So it's actually that x plus 3 halves along with that 5, right? So the big R is x plus 3 halves plus 5. So x plus 3 halves plus 5. So the last one, we should have actually added 1. So if you go back to what we were doing earlier, it's not just x plus 3 halves square, it's x plus 3 halves plus 1 and then square. So now we're ready to write our equation because we have the big R and the little r. So our equation for part D is going to be volume is equal to integral from negative 1.5 to 2, and it's pi, and I'm going to squeeze the pi out here because pi has no business doing itself inside of there. And it's going to be big R, which is going to be the R right there. So it's going to be x plus 3 halves plus 5. And yes, you can put 3 halves and 5 together. You can make it into 6.5 if you want. I'm just going to leave it like that. Square, and then minus, and then the small r, which would be 5 squared dx. Okay? So that would be your equation for your volume. Okay, because remember, all of this right here, that x plus 3 halves plus 5 squared, that's actually a capital R. That's the radius right there. That's big R squared, and the 5 is actually your little r squared. So you go back to what I was talking about earlier. It's just pi times big R minus little r squared. All right, you need to review that. Okay. So let's go one more. Okay, this will be the last one. We'll look at what happens when the line is y equals 10. So I'm going to go back to the beginning. Okay. So you need to go ahead and review any of it if you need to. In order to make that update on part B, because we're adding 5, or excuse me, part B, we're adding one more. So it's x plus 3 halves plus 1, because from the center to the top is actually x plus 3 half, then we're adding 1 to it. Okay, and down here, actually we won't need any of this down here. So this one, if you notice, you look at part C right there, this is actually wanting us to revolve this around the line y equals 10. And if you look at where y equals 10 is, again, our region is going to be this region right here. And we're talking about all of this right here. And if we're looking at y equals 10, it's actually way, way up high. So this one, it works sort of the same as what we've been doing, but it's not exactly the same. So just be careful with this. Okay. So y equals 10. Let's move this to the back. Order, send to the back. Okay. Oh, I lied. Order, send back. Maybe not. Order. Well, that's okay. We'll just leave it there. There. This will be fine. Okay. So part C, we're going to revolve this around the line y equals 10. So if we look at this, so that's no, 1, 2, 3, right? So remember 1 right there, 2's right here. That's this spot right here is 1.5. So 2, 3, 4, 5. Oh, we have to go a lot more, right? So 5, 6, 7, 8, 9, 10, and we are actually going to revolve this around that line right there, y equals 10. That line right there. So this one's going to be a little trickier, so make sure you pay attention. So we're going to revolve it. We're going to spin this region around that. And what kind of shape is it going to make? Very, very fun shape, actually. All right. So first off, if we're going to try to draw that, okay, notice that this is, no, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, and then a little bit more. So what's going to happen is it's going to reflect that up there. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8. Okay, and actually it's not even important that you draw this one correctly. Okay, I mean it is important that you know what it kind of looks like, but it's not that important that you draw it correctly, because this one's, and all of these three-dimensional shape. I mean I'm willing to bet that you're having a hard time drawing it, and there's no real issue with that. You just have to do the best you can. But what's going to happen is that when I reflect this, it's going to end up all the way up here, kind of like this. I'll exaggerate a little bit more, right? I'll exaggerate. So it's going to kind of look like that, okay? And I should be up a little higher, but that's what it's going to look like. And what's going to happen is we're going to revolve this around that. So what does it end up looking like if we revolve it? Right, so it's going to do this right here. Here, I'll put it in red. It's going to, this is going to trace out the front. And it's going to trace out the back, and it's going to trace out the front, the top part. Okay, but all of this, it's going to create kind of like a little hole, a little shallow, or a little hollow. Excuse me, not shallow, hollow. Okay, and the hollowness kind of opens up all along here, because all of this is going to be where the hollow is. Okay, so on the outside, you'll see something like this. On the outside, you'll see something like this, and like this. Okay, and it's going to do this. And then on the front, it's going to do this. So you won't even notice it. If you don't know that it was hollow, you would just look like a solid tube, right? But it is going to be hollow right here to here, and then the hollowness doesn't go straight like how we had it before, like that. Nope, not like that. But the hollowness goes diagonally up, and the hollowness goes diagonally down like that. All right, so that's my three-dimensional shape. And again, it's not very important that you can draw it correctly. I mean, it's just important that you can kind of figure out, what is that what is that, excuse me, what does that cross-sectional area look like? So if I was to cut cross-section, right, so first off, if I was to cut a slice, I would actually, the outside would look like this. Okay, you can cut the slice anywhere. The outside will be this little slice, a little. The inside, or depending on where you cut it, if you cut it towards the very back, the whole thing would be hollow, right? It'd be a very thin piece. If you cut it right in the kind of like towards the middle, like how I'm doing it, you get this kind of little, kind of like the last piece. If you cut it towards the front, it'll be, the hollow will be kind of smaller, or towards the right hand side. Okay, but what you have is, this, and again, it's just going to end up looking just like the last piece, except this one, no matter where you cut it, it's always, the outside will always be thick. Right, the outside will always be a big old piece. If you're doing that where I'm at right now, the inside, the hollowness will look like this. Right, so that would be like in the shadow. And it will end up looking, again, it shouldn't be stretched, but we end up looking kind of like this. Not very pretty, but okay. If you cut it towards, if you were to move this towards the beginning, or towards the right hand side, then this little circle will actually be a little smaller, right? And as you move more towards the right hand side, guess what? As you move more towards the left hand side, the circle here is bigger and bigger and bigger. So if you were to cut it way over here at the beginning on the left hand side, that circle will look like that. And you would go all the way almost to it, then you will have a circle that looks almost like that. Okay? But regardless of where you cut it, and it really doesn't matter where you cut it, let's just put something in the middle here. Okay? Regardless of where you cut it, okay, you will still have a big R and a little r. And now this time around, notice where the original function is. Okay, the original function is way down here. That's the x plus 3/2. That's where the original function is. So we don't want to use a radius and measure from the center going up, because we don't know anything about this top function here. And we don't want to measure from this axis of rotation to the top, because we don't know anything about it. What we do know is the axis of rotation to the bottom. So we want to know, okay, if we cut it right here, right, this wedge right here, What is that big radius? That one's pretty simple, right? That's going to be your big R. So from here to the bottom, and we know that that big R is 10 because that's where my axis of rotation is. That's where it's 10. So we're just looking at where is it from there to there, and then we know that that's 10 already. Okay, so that's the easy part. Little r is the kind of like the slightly harder part. Little r is from here to the inside radius. Okay? Meaning that from here to that dotted line right there. Okay? So from here to that dotted line, or to that line that where the hollowness is. So the hard part is understanding what that little r is. And that little r, you think about on our original graph, if I was to put a little bit more, that would also be 10, wouldn't it? And so that would be the whole thing of 10, but it's not. If we want to use the whole thing, but we want to take out this bottom part. And that bottom part, this distance on the bottom, that's actually our equation. So that little distance down here, that's our x plus 3/2. So little r is going to be 10, but we're going to take away x plus 3/2. So little r, if I can move this over just a tad, it's going to be my equation of 10 minus the x plus 3/2. And I suggest you leave it like that for the little r, right? Because if you leave it like that and you put it into a calculator, if you are going to be working on it, the calculator will figure it all out for you. Okay? If you don't put the parentheses, you will end up getting it wrong. So big R is going to be from the inside to the outside, because that's the big R, the big radius, right? And then little r will be from the axis of rotation to the inside, which would be the whole thing of 10, right? So again, if I was to draw the whole line of 10, oops, I'm green on that one. Let's draw the whole line of 10, it would look like this, right? But what we want to do is we want to erase that x plus 3/2, and that's how we get the small r, or the inner radius. Okay, so now what does that function look like? We'll write it down below. Okay, so that function is going to look like, or that volume equation is going to be volume equals, this is letter C, volume equals, we're going to start off with the integral from negative 1.5 to 2, and remember it's going to be pi times big R squared minus little r squared dx, correct? So we're going to move the pi on the outside, so this is going to end up being pi on the outside, negative 1.5 to 2. Big R is going to be 10, so it's going to start out with 10 squared minus, and little r is going to be 10 minus x minus 3/2. Okay, if you want to utilize the parentheses, that's what you would do, because it's 10 minus both of those, and square dx. Okay, if you want to keep it just exactly like that, you want to write it as minus parentheses 10 parentheses x plus 3/2, close parentheses, then square dx. Okay, you want to write it like how we originally had it in green. All right, all I did was just distribute that negative into the x and into the positive 3/2. Okay, either way is fine and acceptable. All right, so review that last part if you need to. I think this video has gone on long enough. Go ahead and try your best with the practice that I'm going to give you, which is review number, or um, uh, volume of a solid, number 3. All right. So hopefully that helped out a little bit. If not, it's okay. We can talk more when I get back.